Good morning, class. We are looking at section 4.3, how derivatives affect the shape of a graph. First, definition of absolute and local extrema refer to the following. In the case of absolute, it works in the entire domain, that it's the largest or smallest value of y. In the case of a local or relative, it pertains to simply an open interval. Critical point, basically you set f prime equal to 0, where f prime is 0, or f prime doesn't exist. Those are the answers for critical points. Extreme value or closed interval theorem, if you have a continuous function in a closed interval, you evaluate the function at its critical points, the end points as well, and the largest would be the absolute max, the smallest would be the absolute. Rolle's theorem and the mean value theorem. Rolle's theorem indicates if f is continuous in a closed interval of a to b and differentiable in an open interval of a to b, if the endpoints have a functional value that they are equal, f of a equals f of b, then there must be some point in that interval such that f prime equals 0, which means a horizontal tangent line. The mean value theorem, okay, so the Rolle's theorem is a special case of that. If f is continuous in the same closed interval and differentiable in the same open interval, then there is a point somewhere where f prime is equal to f of b minus f of a over b minus a, which means there is somewhere in between that the secant line is parallel to the tangent line is parallel to the secant line. Here's the summary of the section, okay? So let's quickly cover the summary and then we look at the details. The function is increasing, f prime is positive, and decreasing, f prime is negative. A critical point definition was given, find f prime set equal to 0 and where it does not exist. Relative extrema, okay, happens at the top or bottom of an interval, okay? In other words, peaks and valleys. And when f double prime is positive, meaning f prime is increasing, we have a concave up, otherwise it's concave down. If you look at the concept and the graph of a concave up, you'll see what happens here as an example. If you were to draw a tangent line, you would have a negative value, okay? Then it becomes 0, then it becomes positive, so f prime is increasing. And an inflection point is where concavity changes, and probably where f double prime is 0 or doesn't exist. If you look at these graphs, they will help us understand the concavity a little bit better. In the case of a concave up, the graph is above its tangent line. In the case of a concave down, it's below its tangent line. Also look at this one, the same thing that I was explaining before. If you look at this tangent line, okay, the slope of this tangent line, okay, versus this one has a larger slope, and therefore f prime is increasing, okay? But for this case, it's the other way around, the f prime is decreasing. Okay. How do we graph a function? We use the knowledge of pre-calculus. The pre-calculus give us the knowledge about finding intercepts, the end behavior, okay? The end behavior, remember, if the leading term is ax to the power of n, where n is even, it looks like x squared. If a sub n is positive, otherwise looks like minus x squared. If n is odd, looks like x cubed or minus x cubed accordingly. And behavior near an x-intercept, I will explain that with a couple of examples here. Aside from that, we add extrema using calculus by sign graph. So what do? We find f prime, we set equal to 0, we solve, we do a sign graph. By the way, when we say f prime equals 0, also we look at where f prime does not exist. We also find inflection point or points if they exist by getting f double prime and again doing the sign graph to figure where the function is concave up, concave down, and whether we have an inflection point or not. When we put all of this together, we have a decent graph. Okay. Now, extreme values of a function are created when the function changes from increasing to decreasing or vice versa. So the idea of change, increasing to decreasing, decreasing to increasing, take a look at what happens. The change gives us local max when we go from increasing to decreasing, otherwise it's local mean. It's a local max, increasing to decreasing, this is a local mean, okay? And it repeats here, look at it, decreasing to increasing to decreasing. So we have a local mean first and then local max. Same here, increasing, decreasing, increasing, decreasing. So we have a local max, local mean, local max. And so it gives us the definition of increasing. F prime is positive, increasing, F prime is negative, is decreasing. Now, as far as the proof is concerned, the proof comes from the mean value theorem. Everybody remembers that if we have a continuous function and a differentiable function from A to B, okay, then we have this f prime of c equals f of b minus f of a over b minus a, and this one is the same thing. So what happens, okay, as we go from left to right, assuming a is on the left, then b minus a is positive, okay. If f prime is positive, then the product of the right side is positive. So f of b minus f of a is positive, and f of b is larger than f of a. Believe it or not, that's a proof. In other words, b is larger than a, and f of b is larger than f of a. That's the idea. As we go from left to right, okay, that's what happens. This is the definition of increasing, okay, decreasing. All right, so if y prime or f prime is positive, curve is rising first. Take a look. We have increasing, then decreasing. And increasing, just increasing and then decreasing. This is a local max. If it goes the other way around, take a look. So from decreasing, we go back to increasing. Now it's a local mean. And when y prime or f prime is 0, doesn't exist, local possible local max or mean. How do we get there? Sign graph. This is known as the first derivative test, everybody. First derivative test. Let's go to the second derivative. So let's find f double prime, okay, and see what happens. If it's positive, the curve is concave up. If it's negative, it's concave down. Okay, and that would be the possible inflection point. So concave up where f double prime is positive, concave down when it's negative. I showed you the graphs that indicate this. And this is really the test of concavity. I want to make sure everybody understands that. So it uses the second derivative. However, the second derivative test is really gives us the half of the information about the first derivative test. So what is that? I'll go over that in a moment by looking at a couple of simple examples. So we want to do this graph. And what I want to do, I want to show you how we can graph this without calculus in essence. Okay, so let me quickly show you how it's done. So if we want to graph this without calculus, okay, so first, okay, let's just so the idea is to graph it. All right, let's discuss the AND behavior. Okay, now I hope you see that a sub n x to the power of n. Okay, n is 3 and a sub n is positive. So it acts like x cubed, which means this is your AND behavior. Okay, class, you're in the first and the third quadrant. So that's one piece of information. Okay, the next thing is we are going to look at intercepts. I hope you see that it's in factored form so we can see the intercept. So x-intercepts, okay, is at -1, 0, 2, 0. Now, if you look at x plus 1, I hope you see the exponent is 1. We call this multiplicity 1. I hope everybody is remembering this. Multiplicity 1, whereas x minus 2 has multiplicity 2. When it has a multiplicity 1, and let's, by the way, locate those. Okay, let me just. Now, multiplicity 2, we put this notation, meaning it can't cross that. So when the multiplicity is m is odd, graph can cross the x-intercept. M is even, it cannot. So a graph can cross the x-axis at its intercept, x-intercept, if the multiplicity is odd, otherwise it cannot. So having that, that means when it gets to here, it can cross, but not here, okay? And so the next thing is finding the y-intercept. I hope you see that the y-intercept, you replace the x with 0. So if we go with 0, we get 4, and let's assume this is 4. So if we were to graph this using pre-calculus, we are practically ready. So we can graph it like this. So I'm going to show you 3 different graphs. This is one possibility. Okay. The other one is this one. And the other one, in other words, I don't know where my max is, but I know my intercepts. Okay, I don't know when it's going to come back with pre-calculus. Now we're going to add this. I hope you appreciate just giving you the synopsis of what you should know from pre-calculus. Intercepts, behavior near an x-intercept. The concept of multiplicity comes with that, and the AND behavior. So having said that, let's go back to the question. All right, so we want to graph this. Okay, we've already discussed the intercepts, and it's simple to see. Now let's find relative extrema. In other words, we have an idea how the graph looks like. Let's add more. Okay, so it's a simple case. F prime of x is 3x squared minus 6x. You set it equal to 0. you factor and x becomes 0 and 2. I hope it's easy for everybody. This is, by now you have mastered the beauty of differentiation. So again, we have 3x squared minus 6x. Okay, you take the 3x out, x becomes 0, x becomes 2, and now you do the sign graph. So take a look at what happens here. You put the number line, here's the sign graph, number line. You put x equals 0, f prime is 0, x equals 2, f prime is 2. So you pick up a test point to the left of 0 and in between, and so on and so forth. Now, one thing I want to mention, when the exponent is odd on these pieces that you are doing the sign graph, then the sign alternates. So as long as you find one is good enough. But just as an example, you can pick up a test point here, class. If you pick up anything here, let's say for the sake of argument, -1. And what do? You can put it here, or you can put it in the factored from whatever is easier. So if you put it here, you get negative, and then this is negative, negative times negative is positive. This becomes positive. You can do the rest in the same manner. Between 0 and 2, pick 1. After 2, pick 3, or just remember what I told you and why they alternate, okay? When you are dealing with a polynomial of this form and the degree on each case is odd, then they alternate. Otherwise, it doesn't. So just take a test point to be on the safe side. This gives us a lot of information. Wherever you see positive is increasing, negative is decreasing. First of all, I like to put the arrows, and here's the reason. Look at the arrows, up and down. That means at top here, you have a local max. So local max happens at 0. You have to put it back in to find the y coordinate. Down and up. Local mean at 2, okay? And you put it back in. So it's increasing, decreasing, increasing here. And we have a local max and local mean. So take a look. Local max equals 4. Why is that? You put the 0 into the original function. Original function. Now, you put the 2 into the original function, you already know 2 gives you 0. So local mean equals 0 at that pair, okay? Increasing, there are 2 areas. So negative infinity to 0, union 2 to infinity, the rest of it in between is decreasing. So that's what's happening with this function. Now, I'm going to show you the second derivative test, everybody, but don't do that for graphing. Learn it for the sake of applications. Why not for graphing? Because it only does half of the job. I can't emphasize this enough. Okay, everybody? So what is it that it does? Okay, first we have this function. Then we have y prime, and we have the critical points from the previous page. Nothing is brand new. We just repeated what we had from the previous page. Now, we are reminding everybody when f double prime is positive means concave up, f double, and that means relative mean. Remember, concave up, right? Concave up looks like this. Concave down looks like this. And so if it's concave up, you're looking at a local mean. If it's concave down, you're looking at the local max. So I hope you see why this is the case, okay? So let's find the second derivative. 3x squared minus 6x. Differentiation gives us 6x minus 6. Okay, class? And now we plug in. If we plug in, 0 gives us negative. So graph is concave down. Okay, this is where the local max occurs. Now plug in number 2. Plug in number 2, and that gives you positive. Positive means what? Okay, concave up. Okay, relative mean. So what happened? We just got half of the information of the previous page or the first derivative test. That's why you don't want to do that when you're graphing, everybody. Just do the first derivative test. But for applications, you'll see why sometimes it makes it easier. All right, so, but what is the test of concavity? It helps us find the inflection point. We already have f double prime, okay? And we are going to set that equal to 0. And x gives us 1, and we do the sine graph on that. So take a look at the sine graph on that, everybody. Okay, so you put x equals 1 here, y double prime becomes 0. Okay, now to the left of 1, you can pick up a test point. The easiest one would be 0. Okay, and then you plug it into this. I hope you see that if you plug in 0, this makes it negative. Okay, on the other hand, if you plug in to the right of 1, to the right of 1, pick a test point. We are picking up test points. I'm going to call it TP. So we are picking up here 0 and over here like 2 or 3 or 4 or 5. You don't have to pick 3. Okay, I want to make sure that everybody understands. You don't have to pick 3, everybody. Okay, so having said that, let's plug in 2 or 3 or 4 or 5 or any other number becomes positive. Okay, what does it mean? Okay, from negative infinity to 1, negative concave down, from 1 to infinity, positive concave up. Therefore, inflection point at x equals 1. What is the pair? X equals 1, y equals, plug it here. Okay, and 1 and 1 is 2, 1 minus 2 is negative, 1 squared is 1, and that becomes 2, 1, comma 2. Okay, so here's the information we get: concave down, concave up, and an inflection point at x equals 1. Precisely what does it mean? 1, comma 2. Let's put all of this together, everybody. We're going to put all the information together. We have the intercepts. Let's make a summary. Take a look at the summary. We have the x-intercept negative 1, 0. We have the y-intercept, which is also the max at 0, 4. Inflection point at 1, comma 2. X-intercept at 2, 0. 1 extra point of 3, 4, or do not use it, your choice. So negative 1, 0. 0, 4. And we are doing this because we are saying that's a local max. Okay, 1, 2. The next one is 2, 0. And again, an arrow to say this is a local mean. And some other point, let's say 3, 4. If you need, you can pick up a couple more points. No need for that. And then what happens? You put them all together, and that's your graph, everybody. Okay. All right. Here's the function we want to look at quickly. Okay. So let me just quickly give you the synopsis of this graph also. If we want to graph this, first we look at the intercepts. The intercepts class, they are easy to come by. If I factor this off at 1/2 x, or just let's take off x squared. Not that it matters, either way is fine. Class, we can do that. So just x squared, let's say. So x squared times 1/2 x squared minus 1 equal to 0. We are looking at intercepts, okay? So this gives you 0, which means 0, 0. This one gives you 1/2 x squared equals 1, x squared equals 2, x is plus minus square root of 2, and it gives you what you see. Okay. Now, what is that? A sub n, x sub n equals 1/2 x to the power of 4. So this is even, everybody, and this is what? Positive. So that looks like x squared. That's really the idea behind this. I hope everybody's comfortable with that. So if you graph this curve, so in other words, here's the expectation for the end behavior. Okay, that means x squared, y equals x squared, right? And so square root of 2, let's say this is 1. Let's say this is 2. This is negative and negative 2. So it's 1.41, so it's here, and negative 1.41 roughly. Okay, and so the graph, if you just go with that, and you can pick up more points, when it hits this one, it goes down, and it has to come back up because there is another x-intercept. But what happens here, and I want to show you here, over here at 0, 0, everybody, what happens is very simple. Take a look. Multiplicity even. Do you see multiplicity 2, 4, 0, 0? So it has to come back down. Okay, and it has to go back up at some point to hit the next x-intercept, and it goes up. Now, when will this happen? We don't know, but this is the general shape. So I hope you see we can still graph it fairly decent, and of course, if we are doing it with pre-calculus only, we add a few more points. Okay, so we have an idea of what's going on. So let's go to the new question. And so we've already discussed, how we find the intercepts. Let's look at f prime of x. 1/2 times 4 is 2. X cubed minus 2x. We set it equal to 0 by factoring the 2x out. And I hope you see that when you take the 2x out, class, you get 2x times x squared minus 1. And x squared minus 1 is x plus 1, x minus 1, and that's how you arrive at the answer. And so the critical points are at 0, negative 1, and 1. A couple of things I want you to notice. Again, this is all of them have only degree 1. So as long as you pick up a test point for one of them that will do the job, they will alternate, class. So you can pick up test points for all of them, or just to the left of negative 1, for example, negative 2, and observe what happens. If you pick up negative 2, plug it here. Negative makes this one negative 2, makes this one negative, this one negative, this one negative. There are 3 negatives, so the answer is negative. And then they alternate. Okay. By the way, pay attention to number 2. This is positive, it doesn't change anything. But if it were negative 2, then all of these signs will alternate in a different manner, positive, negative, and so forth. So you want to pay attention to the sign of the coefficient. Okay. So what does it mean? Let's look at the arrows also. To me, they are really helpful. Arrow down and up. See, this is the bottom of the graph, local mean. Up and down, local max, local mean. So when I say local mean at negative 1, you have to plug it back in to find the y coordinate. The same thing for the rest of them. So negative means decreasing, positive means increasing. So local mean equals negative 1/2 at x equals plus minus 1. Those are the pairs. How do we know that? First of all, whether you put negative 1 or 1, it makes no difference. Both of them give you the same answer because they are being raised to the power that are both even. So let's quickly do that. 1/2 If you plug in 1 to the power of 4 or negative 1 to the power of 4 gives you 1, so 1/2. Minus either 1 or negative 1 squared is 1, so 1/2 minus 1 is negative 1/2. I'm showing you right here. All right, and then of course 0 is 0, so we have that one. And then decreasing from negative infinity to negative 1 union 0 to 1, otherwise is increasing. So we write it in this manner. So we got the intercepts. We did the first derivative test. We got local extrema, and we got intervals of increasing as well as decreasing. The next thing is to find the inflection point. That means we need to differentiate this again. All right. So here's f prime. Let's differentiate and we get 6x squared minus 2. We factor out the 2. We get x squared minus 3. Okay. 3x squared minus 1, my apologies. 2 times 3x squared minus 1. And x is plus minus 1 over square root of 3. So when you take out the 2, 3x squared minus 1, 3x squared equals 1. This means 3x squared equals 1. X squared equals 1/3. And so x is plus minus the square root of that. So those are the inflection points. The sine graph is easy, believe it or not. Again, there are really 2 roots. That means nothing repeats, okay, class? So that means as long as you find 1, you're in good shape. You can pick a number to the left of this, in the middle, or to the right. I hope you see the middle is 0, right, between negative and positive. So if you plug in 0, you can see what happens, okay? So when you plug in 0, it may be even easier to plug it into this. Makes it negative. So if this is negative, then the other 2 must be positive. Or just pick up to the left of negative 1 over square root of 3, like negative 2 or negative 10. To the right of 1 over square root of 3, positive. All right, so what does that mean? It means over here is concave up from negative infinity to negative 1 over square root of 3. From 1 over square root of 3 on is also same union, okay? In between is concave down. We have we have 2 inflection points. At those 2 points, plug it back into f of x to find the y coordinates. So let's see what happens. So concave down in between, concave up beyond the 2, okay? When we plug in, let's see what happens. I've shown you this is simple elementary algebra. If you plug in 1 over square root of 3 or negative makes no difference. What I want you to notice is this, everybody. This one is 1/3. Okay, so that's what we have here. Now this one is 1/3 to the second power, or 1 over 9, because it has the exponent 4. Now the rest is easy. Okay, so you have 1/2 times 1 over 9, which is 1 over 18, minus 1/3, which is minus 6 over 18, minus 5 over 18. And we need to change all of them to decimals for the sake of graphing, okay? So we have an approximation how they look like. So take a look at what happens. So the IP address, okay, we are changing 1 over square root of 3 to its approximation. This is an approximation 0.6, minus 5 over 18, minus point, let's say 3, or minus 0.278. So what we do, let's write the summary of what we got. So we have 2 points for x-intercepts here, negative 1.410 and positive 1.410. So negative and positive. Then we have the maximum that occurs at 0, 0. Okay, and bear in mind that over here, then it can't cross. Do you follow what I'm saying? I can even do this. Okay, so something like that. Then the IP address, okay, instead of 1 over square root of 3, we put 0.6, okay, because it's easier to see. So, and the other one is negative 0.3, let's say. So this is one of them. Negative 0.6, negative 0.3, positive 0.6, positive and negative 0.3, and then minimum class. Negative 1, negative 1/2, positive 1, negative 1/2. So I hope you see that, you know, you really have to do your best to do this, and sometimes it's not easy, okay? So anyways, now I want to erase this, and you put them all together and it looks something like this. I hope you see that the graph is what we have already expected, but it's more precise because we are using calculus. I want to look at an application to mention really the difference between the first and second derivative test. All right, so the number of bacteria is given. We want to find the initial population. I hope everybody recognizes that this is simple, obviously. Just initial means t is 0. So plug in 0 and evaluate it. Okay, so this becomes 0 because of this t. This becomes 0, you're left with 100. 100 what? Millions of bacteria. At what time before 10 hours will the population be maximized? Means you're looking at this. So in other words, you have over here 10t minus 2t cubed plus 14t plus 100. Combine, put them in descending order, and pay attention to the fact that 0 is included. This is a continuous function, by the way, but 10 is not. Okay, class? It's half closed, half open. So you have to consider 0 in essence we already have. Now the rest, let's do the first derivative test by finding n prime, setting it equal to 0. Minus 60 squared plus 24. And I hope you see that this is a simple case because you have to say okay, let's write it here, equals minus 6 times t squared minus 4, which is t plus 2, t minus 2. There are two answers. And as you can see, from 0 to 10, we can only use t equals positive 2. So having said that, what happens? You do the first derivative test. Is easy, class. To the left of 2, you can plug in 0, okay? And 0 gives you, let's just say, positive here, negative here, but this negative 6, this is what I meant, class. If you happen to have a coefficient which is positive, you can ignore it. It doesn't change anything. But in this case, it does. Negative. Positive, negative, their product is positive. So up and down, local, okay, max happens at t equals 2, okay? Now, we can do the second derivative test, which means the following, and I want everybody to see what that means. N double prime is negative 12t, okay? And now you plug in and observe what happens. N double prime is negative 12t. You plug in because it's negative, okay? It's concave down, occurs at t equals 2. What do? You plug in t into the original function or this one, and evaluation results in 132 million. That's the maximum value. So again, if you don't want to do the sign graph, so class, do the sign graph and you're done. Don't do the sign graph, do this one. I hope you see what happens. So all of this calculation is a must. You need to do all of this. You do either or, okay? Either this one, the first derivative test, or this one, your choice. Don't do both. I think most of the time, the second derivative test is easier. All right. Here's the next graph. And what I want to do for this graph, I want to also give you the synopsis of what's coming up so you have an idea, again, as far as the transformation is concerned. So what we are looking at, class, is this graph. So I hope you realize this is a cube function. So if I'm graphing this, okay, first, so number one, I have a cube root function. I hope you remember cube root looks something like that. Number two, I'm going to call it y sub 2 is cube root of x squared. By the way, this is cube root of x minus 2 squared plus 1, okay? So what happens here, class? This becomes a little bit larger and this flips over, becomes positive. Again, I'm discussing a transformation in essence. Number three, we have y sub 3, let's say, that is cube root of x minus 2 squared. That means it's the same thing shifted to the right by 2 units, okay? This is not to scale, class. And finally, cube root of x minus 2 squared plus 1, it shifts up by 1 unit. So with the transformation, and if need be a couple of points, you really know how the graph looks like, okay? So I wouldn't worry about that. But let's quickly look at it from the point of view of calculus and add things here. All right, so let's see how it's going to look like here quickly. So the very first thing is to differentiate this. This is really simple. We are not too worried about that. By now, we have mastered the beauty of differentiation. 2/3 x minus 2 to the power of 2/3 minus 1, which is negative 1/3, and then times the derivative of the inside, which is 1, plus 1 gives us 0. So here's the differentiation, and we rewrite this. Okay, so that's f prime of x. That shouldn't be a big deal. So what happens to f prime of x? If you set it equal to 0, that means it's a fractional expression. The top is 0. It can never be 0. Doesn't exist, the denominator is 0, and therefore x becomes 2. And you do the sign graph on that. Now notice what happens. To the left of 2, for example, 0. If I put 0 here, I hope you realize this is negative. Cube root becomes negative. The top is positive over negative is negative, and beyond 2 becomes positive. What does it mean? Look at the arrows. Okay, so the arrows tell us that it's a local mean. So local mean at x equals 2. And of course, you got to plug it back in. When you plug it back in, this becomes 0. So you have 1, 2, 1. We already have seen it from the graph that I showed you. Negative means decreasing from negative infinity to 2, increasing from 2 to infinity. So that's very straightforward. Now let's look at the second derivative test. So to do the second derivative, the concavity test, to do that, we need to differentiate this, but it's easier to differentiate this piece. So 2/3, so f double prime, 2/3 times negative 1/3, okay, which gives us negative 2 over 9, x minus 2 to the power of minus 1/3, minus 1, or minus 4/3. okay? And we can rewrite it as such. Now, I hope you see that what's going on here. Let's look at the denominator. Number 9 is positive. Cube root of whatever being raised to the power of even becomes also positive. So the whole thing is positive in the denominator. Negative with the exception of x equals to. At x equals to, it's not negative, okay, class? It's undefined. So f double prime is 0, never. F double prime doesn't exist at x equals to. If we want to do the sign graph, I'll show you the sign graph for one reason only, and that is to be able to write, properly the intervals of increasing, decreasing. Why am I showing you this? If you're looking at this one without writing x is not true, this means it's concave down, okay, always. Does it mean from negative to positive infinity? It would, except when we see x is not equal to 2, that means you have to write from negative infinity to 2, union 2 to infinity. And if you look at the sign graph, everybody, okay, the same thing happens here. Negative and negative, that means concave down, but it's not from negative to positive infinity. Rather, it's from negative infinity to 2, union 2 to infinity. And I want you to pay attention to that, and also what I wrote here. X cannot be 2, okay? That's why you write it this way. Otherwise, if it is concave down everywhere from negative to positive infinity, it is really a smooth curve. All right. So intercepts, if you replace x with 0, you get negative 2 to the power of 2/3 plus 1. Negative 2 to the power of 2/3, that means cube root of 4. I hope you know that, right? So negative 2 to the power of 2/3 plus 1. This means cube root of negative 2 squared, which is 4 plus 1. Okay, again, I put this here, a to the power of m over n is nth root of a to the power of m equals the nth root of a to the power of m. Okay, there are different ways of writing. Okay, there is no x-intercept because you have to set y equal to 0. So if I set, let me use a different color. If I set this one equal to 0, that means x minus 2 to the power of 2/3 must be negative 1. Okay, let's raise to the power of 3. X minus 2 squared becomes negative 1 to the power of 3 is also negative 1, and this has no solutions. Why? Because the left side is squared. Now you put all of this together. So we have the y-intercept, everybody. Okay. Remember, cube root of 4 plus 1 is about 2.6 roughly, okay? Extra 0.12, minimum 2.1, another extra 0.32. By the way, I hope you see that if you plug in 3 here, class, 3 minus 2 becomes what? 1. 1 to any power is 1 and 1, 2, okay? And then maybe a couple more points like negative 1, 3.08. Negative 6.5. If you put negative 6 class with negative 2 becomes minus 8. Cube root of that is 2. Minus 2 squared is 4 plus 1 gives you 5. If you plug in 10, you get the same thing. And 10 would give you something like a point somewhere here. Okay. You put them all together, and that's your graph, roughly.